Friction. Let us return to the example of a body of mass m at the rest on a horizontal table. The force of gravity mg is cancelled by the normal reaction force of the table. Now suppose a force F is applied horizontal to the body. We know from experience that a small applied force may not be enough to move the body, but if the applied force F were the only external force on the body, it must move with acceleration F upon m, however small. Clearly, the body remains at rest because some other force comes into play in the horizontal direction and opposes the applied force F, resulting in zero net force on the body. Therefore, Fx parallel to the surface of the body in contact with the table is known as frictional force or simply friction. The subscript stands for static friction to distinguish it from kinetic friction Fk that we consider later. Note that the static friction does not exist by itself. When there is no applied force, there is no static friction. It comes into play the moment there is an applied force. As the applied force F increases, Fs also increases, remaining equal and opposite to the applied force up to a certain limit, keeping the body at rest. Hence, it is called static friction. Static friction opposes impending motion. The term impending motion means motion that would take place but does not actually take place under the applied force if friction were absent. We know from experience that as applied force exceeds a certain limit, the body begins to move. It is found experimentally that the limiting value of static friction is independent of the area of contact and varies with the normal force approximately, where mu is a constant of proportionality depending only on the nature of the surface in contact. The constant mu is called the coefficient of static friction. The law of static friction may thus be written as Fs less than or equal to mu into n. If the applied force F exceeds, the body begins to slide on the surface. It is found experimentally that when relative motion has started, the frictional force decreases from the static maximum value. Friction force that opposes relative motion between surfaces in contact is called kinetic or sliding friction and is denoted by Fk. Kinetic friction, like static friction, is found to be independent of the area of contact. Further, it is nearly independent of the velocity. It satisfies a law similar to that for static friction. Fk is equal to mu k into n, where mu k, the coefficient of kinetic friction, depend only on the surfaces in contact. As mentioned above, experiment shows that mu k is less than mu s. When relative motion has begun, the acceleration of the body according to the second law is F minus Fk upon m. For a body moving with constant velocity F is equal to Fk, if applied force on the body is removed, its acceleration is minus Fk upon m, and it eventually comes to a stop. The laws of friction given above do not have the status of fundamental laws like those for gravitational, electric, and magnetic forces. They are empirical relations that are only approximately true, yet they are very useful in practical calculations in machines. Thus, when two bodies are in contact, each experiences a contact force by the other. Friction by different is the component of the contact force parallel to the surfaces in contact, which opposes impending or actual relative motion between the two surfaces. Note that it is not motion but relative motion that the frictional force opposes. Consider a box lying in the compartment of a train that is accelerating. If the box is stationary relative to the train, it is in fact accelerating along with the train. What forces cause the acceleration of the box? Clearly, the only conceivable force in the horizontal direction is the force of friction. If there were no friction, the floor of the train would slip by and the box would remain at its initial position due to inertia and hit the back side of the train. The impending relative motion is opposed by the static friction Fk. Static friction provides the same acceleration of the box as that of the train, keeping it stationary relative to the train. The force acting on a block mass m at the rest on an inclined plane r1, the weight mg acting vertically downwards. Second, normally force n of the plane on the block, and third one, the static frictional force Fs oppose, opposing the impending motion in equilibrium. The resultant of these forces must be zero. Resolving the weight mg along with two directions shown, we have mg sin theta is equal to Fs, mg cos theta is equal to n. As theta increases, the self-adjusting frictional force Fs increases until at theta is equal to theta max. Fs achieves its maximum value. Fs max is equal to mu s n. Therefore, tan theta is equal to mu s, or theta equal to tan inverse minus mu s. When theta becomes just like